Yeah, good evening, everyone. So we will wait for 5 more minutes. Let's others join. Good evening, everyone. Can anyone confirm by writing in the chat box if I am audible? Okay. Thanks, Sita. So this is discussion. This is a discussion class for course Design of Photovoltaic Systems, which is being taken by Professor L. Umanand from Department of Electronic System Engineering, ISC Bangalore. And I am Ravi Kumar, a PMRF research scholar at IIT Bombay. So in these classes, we usually solve assignments and like recap the content. So I hope you have gone through the lecture for the week 2. How many of you have gone through? Like you can, whatever I'm asking, you can write in the chat box or you can reply. No one? Have you watched the lecture for week 2? Okay. It's okay if you have not watched them. Okay. Okay, Sita. So I think many of you have only watched the week 1 only. So let's start this class. So in the week 1, so this class, let's take it as a story. We are not like studying this as a course. Let's take a story. Like in the first class, what we have seen the structure of a PV cell. Then we have seen the electrical model of a PV cell. If you have any doubt regarding these, whatever I am writing, you can ask. Then we have gone through the IV characteristics. Then we have seen the parameters of a PV cell. Then we calculated efficiency. Then we calculated fill factor. And parameters we have seen. Okay, so let's start the story like this. There is a solar cell that is nothing else but a semiconductor device which convert light energy into electricity. Then why do we understood the structure, that is a semiconductor device? Then why electrical model of a PV cell? Because we need to find out the performance and many other parameters in order to match with our load. That's why we are talking about the electrical model, because we easily understand in terms of resistance, power source, voltage source, in those terms. Then why IV characteristics? Because this is the main output of a solar cell, and using this IV characteristics we can claim, or we can say that if cell is performing well or not. Like if a person is not feeling good, he is having some health issues, so he will not perform optimal. Same here, if IV characteristics of a solar cell is not good, then that cell will not perform well. Then why parameters? Because every time we cannot draw the full IV characteristics of a solar cell. Like if we have large number of PV module in field, then we cannot go and like drawing the IV characteristics of each and every cell which are installed in a PV power plant. So then we have parameters. In parameters we have like VOC, ISC, PMPP, that is a power at maximum power point, VMPP, voltage at maximum power point, IMPP, that is current at maximum power point. Then efficiency. Why we needed efficiency? Because it is important to find out the size of PV panel which we require for any device, because that will take some area, and regarding this area we need to know the efficiency. That we will do some calculations in some questions as well, even you will see in further classes as well. Fill factor is a derived parameter from this ISC, VOC and VMPP, IMPP. So this was the first class. Now I just want to ask you one question, very simple one. Now we were talking about a PV cell. Let's draw a PV cell, standard PV cell like this. The size of this PV cell is 156 mm into 156 mm. Now, can you guess the voltage, or we can say VMPP or VOC, anything, or current, ISC? Can you tell me the ISC and VOC for this device? for this solar cell? Any guess you have? What is the VOC of a solar cell? Single solar cell. This is a solar cell. I'm asking the VOC of this solar cell. The dimension is 156 into 156 mm. You don't know? It's okay. If you don't know, you can write we don't know. It's okay. If you know it, you can write the answer. Okay, let me tell you, it's around 0.56 volt. And ISC, so generally for the crystalline silicon solar cell, we have a simple term, that is current density. So it is like 0.035 ampere per centimeter square. So you can convert it, multiply with this 15.6 into 15.6 centimeter square. So using this you can calculate, it should be around 7 or 8 ampere. So this is the standard output of a solar cell. So let's say 0.56 volt and 7 to 8 ampere is the standard output of a solar cell. Now let me know, why do you want to use solar cell and in which application you want to use? What is the motivation behind studying this course? Do you want to run the appliance which you have in your home with the solar PV? Where do we use this solar PV? Have you seen the usage of solar PV anywhere? No. Giri said no. Okay. See, okay, let's say we have a battery. Have you to use more renewable energy source? Yes, Sita, you are right, for more renewable energy source. And let's say we want to charge a battery, and using this battery we want to run the inverter and then fan and cooler, whatever we want. Let's understand this way. So let's say this is 12 volt DC battery. Have you seen these kind of batteries? 12 volt DC battery? Yes. Okay. But let me know one thing. If the output of the solar cell is connected to this battery, will it be charged? Will this solar cell will be sufficient to charge this battery? No, not at all. Why? Because it is 12 volt battery. Here potential difference is 12. Yes, Abhinandan, you are right. So it says here battery voltage is 12 volt. Yes, Sita is also right. It should be sufficient for charging 12 volt. Rasmi, you are right, compatibility, but like we are looking in the more technical terms. Yes, it is 12 volt and it is just 0.56 volt. So using this 0.56 volt, we cannot charge 12 volt battery. So this voltage for charging a battery, the voltage should always maximum more than the this 12 volt. This is the first rule here. Okay. Now second question. If I cut this solar cell like this, so I am having like this solar cell, it is 156 mm here, and let's say 78 mm here. So what will be the voltage and current like ISC and VOC? Any guess? We have seen for a complete solar cell, voltage will be 0.56 volt, current will be 7 to 8 ampere. But for half cut cell, what will be the voltage, VOC and ISC? We are cutting a solar cell in two parts. See, VOC is not having any kind of formula regarding the area. So VOC will not depend on the area of solar cell. It means VOC will remain constant. So here VOC will be 0.56 volt and ISC half. Yes, you are right. ISC will be half, let's say 4 ampere. So now we understood the voltage VOC of a solar cell does not depend on the size of solar cell, while the current directly depend on the size of the solar cell. Okay. Now I just want to ask you one question. We have a battery which we were talking about, 12 volt DC battery, and let's say 2 ampere is the current. So if we have a one cell which is having 0.5 volt and 8 ampere current, how many solar cells we need to charge this battery? Minimum number of solar cells we need to charge this battery. Minimum number. Maximum though we can get anything, but minimum. (24). And those 24 solar cells will be connected in series or parallel? Series, because in series, yes Vikas, Abhinandan, you are right, in series the voltage will add up while the current will remain constant. So from here we got our motivation for the today's lecture, that is series and parallel connections of PV or solar cell or module. So this is the motivation behind this today's class. And now you got it why we are studying series and parallel connections. Because for an application we need, like single cell is not sufficient, so we need multiple cells and multiple modules connected in series or parallel combinations. That is clear. Okay. So regarding the series and parallel connections, first question comes. If we have two solar cells, let's say 1, 2, and 1, 2. These are the two solar cells, 2 and 2, 4 solar cells. We are connecting these two like positive, negative in series here for simplicity. And here we are connecting them in parallel. So positive in, it's like so these are our outputs. Now question comes. We have seen the IV characteristics of a single solar cell. In terms of this series, this is the series, this is the parallel. So the combined IV characteristics of a solar cell while connected in series and parallel, how will it look like? So the total output V, let's say V1, I1, V2, I2. Let's say V1, I1, V2, I2. V and I at output, V and I at output. How much it will be? For the series case, what will be the output voltage? Yes, because it will be V1 plus V2. And the current? Current in series remains constant. So it will be equals to I1, which is equals to I2, because we are talking about the identical solar cells. In case of a parallel connections, what happens in parallel? V1 equals to V2, yes, V1 equals to V2, and current will add up, yes, I1 plus I2. So this is the basic thing, connecting cells in series and parallel while cells are identical. Identical means the voltage and current are same. Here you can see this is the like series connection, and this will be the IV characteristics. So here what is happening, current is remain constant while voltage become double, like V1, V2, so it is double. For the parallel connection like this, we have voltage like V1 equals to V2 and current is double like I1 plus I2. So these are the characteristics of solar cells while they are connected in series and parallel. Now we were talking about the identical solar cells. But what happens when those cells are not identical? Means the current and voltage are not same. That we will see. Before that, we have a small concept, that is load line. So this load line concept is very important, and using this we can trace the IV characteristics of any combination of the solar cells. So it is like that we have solar module or solar cell, and like one load is connected. So here load is R naught. That is the resistance of a R naught. So in this IV curve, if we draw a line like this and we get the slope anywhere, so this slope will be equals to 1 upon R naught. And this is known as the load line. At this point, what will happen to the load line? At this position, what will happen to the load line? If we are moving downward, this delta I will decrease and it will become 0 at this point, at this axis. And if delta I is 0, then R naught is infinite. Yes, Abhinandan, you are right, it's infinity, we can say. So this point is our VOC, because that is the open circuit. Same thing if we are here at this point, then delta I by delta V, here delta I was 0, here delta V will be 0, and if delta V is 0, then R naught will be 0. Yes. So here R naught equals to 0, it means short circuit. So it is ISC. So you have seen, using this resistance we can trace the entire IV characteristics of a solar cell. So this is a one crude way to trace the IV characteristics. Just change this resistance and you will get the entire IV characteristics. So this is the concept of load line, and this is visible here again. R naught 0 ISC, R naught infinity, that is VOC. So this is all about the load line. Now let's move to the non-identical solar cells. I'll cover this quickly. So we have non-identical solar cells like this. We have cell 1, cell 2, they are like having red and green color. It means they are not similar, we can say. So here voltage is VT1, voltage is VT2, and this is the entire circuit. Then the combined cell characteristics should be like this in case of a identical solar cell. This is for identical. But for non-identical, it is like that. One solar cell may have different current like this. If I draw on this curve only, let's say 1 and 2. So these are two different cells having this difference in the ISC. So this is the physical understanding. It means this is the way we trace the IV characteristics. But there is a thumb rule. Like if they are connected in series, then the circuit will follow the current which is lowest. It means the output will be closest to the lowest current. Let's say if it is 8 ampere, it is 6 ampere, then current here will be about 6 ampere only. So this is basic thumb rule. It means the cell which is generating less voltage or less current will limit the entire output. Similar thing happen with this parallel connections. Here also, if those are not identical, so there is different in VOC, and this difference leads to the VOC of the lowest or lower cell. It means low current or voltage dominates. But what happened due to this? Due to this, the other cell become a sink. It means the other cell will be consuming energy there. And if other cell is consuming energy, then what happens? It can degrade. So there may be some defects and degradations. So to prevent those solar cells from being degraded, we use bypass diode. So it's like we can protect these combinations using this is the same thing, using the bypass diode. If we just connect a bypass diode, this is the bypass diode. This green is a solar cell which is connected in series, and this is the bypass diode. It means using the bypass diode, we can prevent the cells being degraded. But let me ask you one question. The cells which are there in field, those are identical or non-identical? The cells which are being used in the field or being used in the manufacturing power plants, do they have identical characteristics or non-identical characteristics? What is your guess? Identical, near identical. Identical. See, identical, it's like a ideal concept. Even if we are generating two things using the same machine, there will be some difference in physical properties or electrical properties between the cells. That's why they are nearly identical but not absolutely identical. I'll show you in the next class some curve which is showing like how the solar cell differs in the same module. If I have one, okay, I'll show in the next class. So there is a like EL characteristics. Using this EL, that is a electroluminescence imaging, using this we can identify the solar cells if they are generating same output or if they are identical or not identical. And in physics terms, we say there is cell to cell mismatch. So this cell to cell mismatch is already there. It is always there. cell to cell mismatch. Okay, now let's move to some questions. So first question says, if we are wiring multiple photovoltaic cells in series, then what will be the answer here? There are two blank spaces and you need to choose two options. What is there and what is there? So simple. If we are multiplying photovoltaic cell in series, yes, Abhinandan, you can retry. C and B, or we can say B and C. Yes, Vikas Mishra B and C, Sita, yes, also B and C. Yes, current will remain same while increase in the voltage will be there. B and C is the correct answer. Next question. So we were talking about the series and parallel connections. So this question is directly based on those concepts. So a photovoltaic panel has three modules. So let's say three cells connected in series. Each module having VOC 20 volt, ISC 5 ampere. What should be the VOC and ISC of the complete panel? And these are the options. Sita said D. Ruchi said D. Vikas Mishra D. What I told you just before the two slides, according to you, both will increase, voltage as well as current. But is it so? In the previous question itself, we have seen voltage will increase but current will remain same if we are connected in series. Sita, Ruchi, Vikas, Prabhakaran, what do you think about this? The last question we did. In series circuit, current will remain same, voltage will increase. In the next question, I am asking this in terms of an numerical. Oh, thick. Then fine. I was looking into E. Okay. Yes. My bad. So it is 60 and 5 amp. I was thinking there are only four options and you are selecting this one. It was my bad. Sorry. So yes, 60 volt and 5 amp. Yes. It is D. Next question. Next question is very simple. It says there is a circuit which need to implement as a PV emulator. What is the load resistance value in ohms which maximize the power transfer from DC voltage source to the load? It means we need to identify this R load when power output is maximum. Also calculate. So I was doing this question other way as well. Load resistance plus P max. What will be that P max? Calculate P max as well. Even the options I am having for the Pmax only. So yes, Pmax as well. $31.25. Am I wrong? Parvakaran said A. Ruchi, you can like recalculate, because if you are saying 31, I think factor of 2 is missing. If Prabhakaran is right, then there is a factor of 2 is missing. What others say? Someone please verify if Ruchi is right or Prabhakaran is right. Is it so? Let me calculate then as well. You are saying 20, and then we can simply say I square R, and I will be 50 divided by 40 square into R. So it should open R load for the Therion resistance. You are getting 31.5. Yes, my bad. Okay, 25 into 5 divided by 4 is 31.25. So it is factor of 2 is there. Yes. So it will be 31.25. Even if you will calculate this by I square R only, then you will get this. So option A is correct. Fine. Okay. Let's move to the next question, which is question number 4. It says the PV module is connected to a load This is the picture which is being shown here. One picture is this, and like with this electrical circuit, this is the picture here. It says what is the value of current flowing in the diode component of equivalent circuit under maximum power point and standard radiance 25 degrees Celsius temperature condition. So it means this ID, you need to calculate this ID at maximum power point. The other part of the question, just say the values, like this is the formula for current across the diode. I naught is a dark saturation current whose value is given here. So in this formula we have VD. So VD is the voltage across the diode. VT is the voltage that is equivalent to the temperature and given by this formula. And in this formula, N is the identity factor, which is 1 here. K is the Boltzmann constant, values given here. T is the operating temperature, and N cell is the number of cells connected in series, and which are given here. And Q is the charge of the electron, which is given here. So these are just the given values. Don't be afraid by seeing the question's length. It is just a 2-line question. You need to calculate this ID, current through this diode. Formula is already given here. I write this here. ID equals to I naught exponential VD by VT minus 1. And VT is given here. VD is the voltage across the diode. I am just giving you the options. These are the options. Calculate it and let me know. Simply just put the values in this formula. I naught is given, VT is given, VD calculate. First calculate this VD, then calculate ID. 2-step problem. First calculate this VD. What is the value of this VD? Voltage across the diode. How can you calculate this VD? Do you want some hint? Do you want some hint? Are you trying this? Yes, no? Okay, I will give you just a small hint. This is V across RS and this is our V. So VD will be equals to V plus V across RS. Let me know if you need some hint, more hint. If you want to know the approach. Let me know if you are solving unable to approach. Okay. See, this question is asking ID at maximum power. It means this voltage you need to take VMPP, and this voltage will be voltage across RS. So our VD will be equals to VMPP plus RS into IMPP. Already given. RS we already have, IMPP we already have from this table, VMPP we already have. Just using this calculate VD, put this VD into this here, and then you will get the answer. Now try. Understood? See, the voltage across the diode will be equals to the voltage across the shunt resistance, and voltage across the shunt resistance or diode will be equal to the sum, that is the voltage across the series resistance plus voltage across the load. Voltage across the load is already given in the question, which is given at the maximum power point. So VMPP will be the voltage across load, and voltage across RS. See, the current which is flowing through the load will be same as current flowing through the series resistance, and at VMPP or maximum power point, that current will be IMPP. So if you will multiply IMPP, yes, Sita said VD equals to 32.94. I thought this is right. If others will verify, then it's fine. Solve further. Vikas Mishra also saying right. Okay, so I think if both of you are getting the same answer, so this VD will be 32.94. Absolutely right. That other than that, you just have values, all the quantities there. You just need to put them there and calculate it. Or Bakaran also calculated VD 32.94. Okay. So now it is verified already that this value is correct. In VT, VD already calculated. In VT, where N is 1, value for K is given. T is 25, which convert into Kelvin 298. Then N cell is already given 60. Q is 1.6 10 to minus 90 coulomb, that is given. And K also given, that is Boltzmann constant. You do it, I'll tell you a short formula as well. So how much VT you are getting? I think you should get this VT. So simple, okay. Sita Vikas VT 0.3076. Have you converted the temperature into Kelvin? Then only you are getting this. And KT by Q. Okay, let me calculate as well. Others also do so. It is Ruchi Vikas 2.468, Ruchi 0.256. See, I got 3 answers there and all 3 are different. Like much difference is there. I am also doing. No, all are not correct. I don't know why you are not getting this. You just need to multiply 3 things only. KT and then divide by Q, and it's simple, that is 60. I got the answer and this answer is right, but yours answer is not right, not Ruchi, not Vikas, not Prabhakaran. What is the issue? Like 1.38 into 10 to the minus 23 into 298 into 60 divided by 1.6 into 10 to the minus 90. Just do this. Yes, just do this. If we just cut this out, so it is like this, into 10 to the minus 4, then 1.38, into 60 into 298 divided by 1.6. 5421.5 equals to 1.5421. This is the VT which I am getting. Now use this VT and calculate ID, and if you are having problem in calculating this VT and if you want to ask anything, you can ask here. Now do so. ID will be equals to 3.43 into 10 to the power minus 10 exponential. VD is like 32.94 divided by 1.542 minus 1. What is ID? Sita, have you got this? You asked to explain, right? Are you guys calculating? I'm waiting. Point 648, Saurav said. So according to Saurav, B is the option. Okay. What about others? This question was very easy. I don't know why you are taking so much time. Sita, according to Sita as well, it's B. Prabhakaran, Vikas, Ruchi. Are you guys calculating? Okay. It's fine if you are not getting answer, you can do it later as well. And if you need some help or you want to ask some doubt here, you can ask. Yes, the answer is B. That is 0.57 to 0.7. 0.5 to 0.7. And like one thing which I told you, I'll give you the best thing. So VT is given here as NKT N cell divided by Q. So remember one thing, this VT without this N and this N can be written like this, N cell VT, that is a thermal voltage at room temperature, and this VT is always equals to 0.026 volt. So you directly can use 0.026 into N if it is being asked at the room temperature condition or standard temperature condition, that is STC. So at 25 it will always be equal to 0.026, or we can say 26 millivolt. So if you use this way, then you don't require this Boltzmann constant like this charge, electron charge, or what are others, and temperature. You don't need to calculate those things. So it is being already calculated at the room temperature. Vikas said 0.65. Yes, that is absolutely right. B is the answer here. So we are done with this question. Let's move to the next question. So very basic question. Among the following, which statement is correct? And these are the options. The first option says the value of diode current. What is the diode current? Which we calculated just now in the previous question. So it is asking the value of this diode current is maximum under short circuit condition and minimum under open circuit post condition. Second option says this is minimum at short circuit condition and maximum at open circuit condition. Third says it does not change, and D says it is diode current is always near to 0. This notice it is always near to 0. So which options do you think is correct here? B. Sita said B, the value of diode current equivalent is minimum under the short circuit condition and maximum under the open circuit condition. Okay. Others? For you guys, I can draw the IV characteristics like equivalent diagram. A, okay, interesting. Sita said B, Rasmi said C is constant under any condition, and Gaston Vikas said A, okay, it means maximum under short circuit condition, minimum under open circuit condition. And Rochi said C, it does not change at all. Okay. So that's why I am drawing this equivalent circuit diagram. So this is ideally 0. So it means RS can change. And if we short circuit this, and if this is 0 at one condition, then current will go through the lowest resistance path. So the current which is being generated here, it will go towards this lowest resistance path. So it will not follow this path at all. But if this is not 0, this is like increasing towards some value, then some current will definitely go there. It means if this is infinite, or we can say open circuit condition, then ID will be the maximum. And if it is short circuit condition, then ID will be minimum, or this minimum can be 0 as well. And using this, which option is right? Maximum at open circuit condition and minimum at IS, short circuit condition. B. Sita said B. Only Sita is right. If you have not understood, let me know. Let's say there is no RS. Then current through this ID will be 0, and that is the minimum. It means under short circuit condition it will be minimum, under open circuit condition it will be maximum. So B is the right answer. Understood? Yes, no, maybe. So correct answer here is B. Let's move to the next question, which says we have 4 non-identical PV modules, which are representing P1, P2, P3, P4. The cell are having 70s, 50, 80, 40. So for P1 it is 70, for P2 it is 50, for P3 it is 80, for P4 it is 40. So these are number of cells. What is the open circuit voltage? Means here, if this R is infinite, what is VOC? What is given there? The open circuit voltage of PV cell is given as 0.615 volt, and ISC is different. It means they are non-identical solar cells. The ISC given for P1, P3 is 8.6. So here ISC equals to 8.6, or we can say pH, that is equals to pH, or here IPH equals to 5.6 ampere. Now you need to calculate the VOC, and these are the options. Vikas, Sita said 73.8, Vikas said B. Okay. How did you calculate it?
So actually, PV1 and PV2 are in series, and this combination is in parallel with PV3 and PV4. Both count for both PV1, PV2, and PV3, PV4, both combination. The number count is 120, and each cell voltage is 0.615 volt. So number of cells multiplied directly with open circuit voltage of each cell, and both number are equal. So the voltage around open circuit connection will be 120 into 0.615, that is equal to 73.8 volts.
Yes. So Sita, Vikas, Rasmi, Ruchi, all are right. Number of cells multiplied by VOC of the cell, because all are connected in series. And then these two arrays are connected in parallel. So one series combination, that is PV1 plus PV2, the VOC will be equals to PV3, PV4. And total VOC in this parallel combination will remain constant, that is 73.8, and it is like B. So B is the correct answer. Let's move to the next question, which says a PV system, means we need to run a 3 horsepower shaft power, which is a DC motor. Efficiency of the DC motor is 82%. And there is a module with 36 multi-crystalline silicon solar cell, and they are like having 9x4 matrix arrangement. The cell size is this one. The cell efficiency is given. If the global radiation is 945 watt per square meter, you need to find out the number of modules required in the PV array. It means, let's assume this way. You have a motor at your home which consumes 3 horsepower power. The efficiency of motor is 82%. Then you have a module which is having 36 multi-crystalline silicon solar cell connected in series, and the cell area and cell efficiency is given. You just need to calculate how many modules you need to run that DC motor. Understood? Requirement is given Generation from cell level is given. Then you need to calculate how many modules you need. These are the options. First steps towards the photovoltaic design. This question is it. Power output at cell level is given. Number of cells in a PV module is given. The motor requirement is given. You need to match the things and need to find out the number of modules you need. If you need any hint, any formula, let me know. How much watt in 1 horsepower? Okay, Sita calculated 27. Okay. $746 watt. Ruchi calculated 41. So from the answers, Ruchi is expensive as compared to Sita. Sita said 27. So we need how many more? 14 more modules in case of Ruchi. What is motor requirement? Yes, because there is an efficiency, so 0.82, 0.82. This is the actual motor requirement. Two seven two 29.27, right? 2729.27. Yes, Prabhakaran, you are also right. Then power output of a PV module at 945 watt per meter square equals to power of cell into number of cell. Number of cell is already given 36. What is the power of cell? Efficiency 12.5 divided by 100 into 945 into area of cell. 125 into 125 divided by 10 to the power 6. So this is a power output of a PV module. How much it is? How much power output of a PV module? Yes. Saurav, you are right. 66.44 volt. Then number of modules required equals to motor requirement divided by P module. 2729.27 divided by 66.4. Approximately yes, so 40. Prabhakaran, you are right. So Sita, have you got the error? Why did you got this 27? I hope you understood. You may be missed some term. Okay. So 41 is the right answer here. Answer is C. Next question. It is very easy. It is from the class only. If you have not gone through the class, then it may be difficult for you. So it says, let us look at a method where we will be able to see the IV characteristics on an oscilloscope. So far, let us draw a circuit diagram as shown in figure. Figure is given here. This is the PV module with the protection diode. This is our PV module, and these are like protection modules, diodes, both series and parallel. This one is parallel one, this one is series one. If we connect in series, then this will work. Let us terminate the PV module now across the terminal. Allow us to draw now not a load but our voltage source. Means we are connected it with a voltage source. Just we did in simulation exercise, then incorporate a series resistance here called R sense. So we have put it in R sense, that is the resistance across which we can calculate V sense and then calculate the current I. So here it is, we are utilizing this R sense to calculate the current. Here VT signal acts like a sweep for the external triggering of the oscilloscope. Therefore, the amplitude should be related to the amplitude of a PV module voltage. It is saying about this voltage. So the amplitude of this voltage, like this maximum amplitude, should be equal to the module's VOC or amplitude of the PV module. So what will the voltage source characteristics be incorporated as load in the circuit diagram? It is simply asking what properties should this voltage have, or what characteristics this voltage should have. And these are the options. It should be unidirectional in voltage without having the capability of sinking current. It is saying without having the capability of sinking current. It should be a bidirectional in voltage, bidirectional. It is saying unidirectional in voltage and current, capable of sinking current. And then last option says bidirectional without having the capability of sinking current. So what do you think? C. C. Yes, Rasmi, you are right. Actually, if this is voltage 18 volt, let's say, and this is 0 to 18, then the direction of this voltage is like this, and this voltage and current or voltage direction is like this. So it is like suppressing. But when this will become negative, it will add up and the current will flow this outer circuit, and it will be a large current because both the voltage will add up. So that's why it should be a unidirectional and also capable of sinking current, means extra current it should sink in. Otherwise this resistance can blow up because large current can flow. So yes, this is the right answer here, capable of sinking current and unidirectional. Option C is right answer. Next we have similar question. If we have a voltage source having the characteristic same as question 8, means last question, we can give the terminal voltage VT value to the external trigger of the oscilloscope and capture the voltage across the R sense and give it to one of the channel of the channel A, channel B of the dual channel oscilloscope, that we could see the XY plot or the IV characteristic of the photovoltaic. See, it is just saying one thing. Using this circuit, we are creating these type of signals. One thing is here, and other thing is that using these points A, B, D, E, let's say this is D. Using these points, we are trying to get the IV characteristics on an oscilloscope, because here this voltage is changing, like we can change in the simulations. So in experiments also we can change this voltage using this particular circuit. So it is just asking about the points at which we need to connect the probe. So let's continue the question. Instead of a source there, we will put a transistor and drive it with a base drive resistance and a diode there to pass only unidirectional voltage. So for this case, the like this may be like this as well. No, nothing to worry. The auto transformer input is connected to 230 supply and step down transformer with ratio 230 to 18 supply. It is just saying about this circuit with BJT collector emitter terminals on in figure. We don't have differential probe for measurement. Which are the following probe connection point for ground probe, measurement probe and triggering probe respectively the correct way for IV characteristic measurement? It is just asking where should be the ground in this point B, A, D or E or C. Where should be the ground? Where should be the measurement probe and triggering probe? It is asking this only. And these are the options. First is ground probe. Second is measurement probe. And third is triggering probe. So simple thing, if we need to get IV here, so ground should be this one. So D should be the ground. Then measuring and triggering, because we are getting like current from this R sense, so across this we can measure and we can using this circuit as a trigger, so we can use this B as a trigger point. So answer here will be A. If you have not gone through the lectures, you should go to yes. Answer here is A. Next question on the same line, it says the figure show the block diagram of a PV emulator. It means we don't have a PV module, but we are using some components generating the same IV characteristics as we should have from the PV module. So that is the mean of PV emulator here. And we are doing with this DC-DC converter and this like PI, PWM and DC-DC converter. The reference current for this is the reference current. So what we are doing, this is a I and V value we already have and correspond, like this I is the reference value. So corresponding to this VT, this voltage value, this gives some reference I value. This reference value is I given to this PI and this PI controls the circuit. So this way we can generate the all values of VI IV characteristic of a PV module. So this is like already we have a table in which we have V and I value. So corresponding to any V, we will have a one I. This control circuit will match the I and according to it will give the output. So here it is asking, suppose the PV emulator is working for the particular node R node. Let's say this is the output circuit or output of this circuit, and this is the load connected, that is R node, and it suddenly increase. So if R node will increase like this, R node is infinite here, so it will go down. And let's say 0.1 was the first condition, while R node is increasing, this 0.2 is the second condition. So due to this, R node or increase in R naught, our I decreases. I is decreases. So here I decreases. So it is asking about what will be the reference current generated by, what will happen to this reference current, and the error seen by this PI controller. You can see here as well, this reference current I T will decrease. Here also you can see this is going down. First I was here, now this is here. And also here, first I, second I. So this IT should decrease. Okay, so these are the options. It says the reference current becomes lower, the reference current becomes higher, the reference current become lower, the reference current become higher. So first thing is clear. Acha, okay, Sita. So see, you understood this circuit or not? Did you understand like why we are having this complex circuit? Okay, I just want to tell you one thing. This is a pseudo PV module. It means a circuit from which we can get the IV characteristics similar to PV module. But how can we get this? We have IV values. IV values we can generate using the IV equation. From those values, if we know the V, then correspond to this V we can get the I, right? And this I can be given to some controller, and according to this I, it can manage the circuit to work in that condition. It can match the I, that is a current. We are having some other V here, then it will have some other I, and this controller will match this I again. So this is the way we can generate complete IV characteristics. Let's say first there was some V here, V1. First we have V1 corresponding to I1 was here as a reference value, and this controller circuit gave us I1 again. Then this R naught has been changed. Then we can say we get V2. Then corresponding to this V2 we will have some I2, and this I2 is the reference value. Using this reference value, this control circuit will give us I2. Then we have V3, it will give us I3, and then this control circuit will give actual I3. So this is the way it works. The question is just asking one thing: if R naught is changing here or R naught is increasing, this is the IV characteristics, this is the load diagram. Let's say R naught dash, and this is R naught. So from this we know R naught is greater than R naught dash, because in this way if R naught increases, this load line goes to down. So from here we can understood that if R naught is increasing, so it was I1 and it is I2. This is the new current. So if R naught is increasing, then what will happen to the reference current? First question is that. So clearly we can say reference current will decrease. Understood? So if R naught is increasing, yes, Ruchi.
Sir, I have a doubt. If the load is increasing, that means the resistance, the load resistance will decrease, no?
No. Resistance.
And suddenly the load to the PV emulator is increased.
Yes, that is 1 by R2. Yes, definitely.
Sir, then the current will increase, that reference current will increase and the error becomes positive. Is that the correct thing? I'm thinking.
See, if R naught is increasing,
R naught will decrease or increase? That is the doubt of mine.
Okay. I got your point. It is 1 by R naught. Yes. Sorry, it is 1 by R naught. And if 1,
Okay.
yes, it is 1 by R naught. What is this load here? What is the load here? See, VOC, what is the VOC condition? At VOC, what is the resistance or load resistance value? Infinite. Abhinandan said infinite. So it means if load is increasing, then this line will go down definitely. So let me tell you one thing. Load here is 0. Load here is infinite. If one point is here, one point is here, so it means load is increasing this way. You understood this?
Yes, sir, a bit.
Yeah. So if load is increasing this way, first it was I1, then it is I2, then this current is decreasing there. Because I1 maximum here. And if load is increasing, this I is decreasing. Any doubt here? Okay. Okay, Ruchira. So this is the reason why this reference current will decrease. So it is saying higher, so this is not the right answer. It is saying higher, this is not the right answer. Now comes to other thing. The other part, that is the error seen by this PI, means the controller will see the difference. What will be the difference? Negative or positive? So here you can see this is the IT which is coming from the circuit directly, and this is the reference IT, and it is like in the positive, it is in the negative. So it's like IT star minus IT, and if IT star is decreasing, then will it be negative or positive? First condition, I star T was equals to I star T. It was the condition first before increasing the resistance. Yes. Then situation arises, then this IT goes down. So I star T minus IT will be negative. Negative. Okay, I got the answer from Abhinandan Rashmi. Yes. So which one will be the answer here? Not A, because it is saying 0. It should C. Yes, answer is here C. So the reference current will decrease, and because it was matching with the reference current, and if reference current is decreased already, then the current minus from the reference current will be negative. Then the error seen by the PI will be negative. Okay, so we are done for today. We will meet in the next class, that will be on the next Friday. And I will upload this video on the YouTube as well. You can access the video later if you need some help regarding lesson 4. Or if you are having some doubt, you can. Yes, Abhinandan. So this is the YouTube channel in the chat box. So this is the YouTube channel. all the recordings from every session you will get there, and just after this class I will upload this class as well. And even if you are having doubt, you can ask in the discussion forum or in the comment below the video. You are welcome, Abhinandan. Thank you, everyone. We'll see you in the next class, that is next Friday. If you don't have any doubt, you can leave the class. If you don't have any doubt, then I am ending this class in the next 1 minute. If you have any doubt, you can ask.